series of events. And this is our foundation founder from back in 2005, Dana Smith. Hey, everyone. And our special guest, Dr. Jon Kaufman, our So while we're waiting for people to come in, we still have quite a few that plan on coming. I'd like to give the opportunity for each of you to introduce a short bio on what you do and which organization. We'll pass around this mic if that works. We're going to start with if you don't want to do anything, you have to do it. We'll start with Aaron.
Okay, hi everyone. I'm Aaron. The chair for Python and I'm so happy to see you guys here. And what I do, we're working at a startup called 2Pi Data Intelligence, not artificial intelligence. So, I'm really excited to be here and I hope we'll have a great meeting.
Okay, hello everyone. I'm Jake, web dev at Time Shift. I'm also a co-organizer from the Pi Data Ghana, and I really like Python and the whole data science ecosystem, so we're here to engage. Thank you.
Hi, I'm Keith. I'm an accountant, and all this is new to me, but I'm an enthusiast all that today, so I go in this process.
Hello, I'm Michael. I'm a pharmacist by profession, but I have a background in health informatics. I'm also new to Python and I really want to learn more.
Hello, I'm Peter, a full-stack web developer, but I'm transitioning into machine learning engineering. Yeah, so I'm here because this data science meetup and there's lots I can learn.
Hello, I'm also Francis, as co-organizer for Python Campus, and also a volunteer for Global Code. I'm a data science enthusiast. That's why I'm here.
I'm also Charles, and I'm interacting consistently. So I'm because of this constant, so I'm ready to learn more.
Hi everyone, I'm Ayemon and I'm into IT and networking. Product is new to me now, so yes.
I'm Geoffrey Delali. I'm a health personnel and I'm a data enthusiast and I'm here to learn more.
Hi everyone, I'm Kodadro. I'm a computer science student, my third year. I'm also a data science enthusiast, here to connect with people.
Okay, give me a few minutes.
My name is Salami. I'm a student. I'm studying statistics and I'm excited about data science.
My name is Mohammed Sadat. I'm a statistics teacher and I'm just curious about data science. I want to learn more.
Hi everyone, my name is Daniel. I'm an IT user, data enthusiast. I have a background in Java programming, but since I found Python, I fell in love and I want to learn more about Python.
Hi everyone, my name is Robert and I'm interested in data analysis. I'm an accountant and I'm here to learn more.
Good afternoon. My name is Andrew. I'm here for a few minutes. Well, I'm a software developer and I hope the data science will be made easier today. Thank you.
Hello everyone, my name is Kafi, a member of Python Community Ghana and lead and organizer for Python User Group. I'm a freelance software developer and I have interest in data science and AI.
Hi everyone, I'm Afi and I'm a recent graduate from K University. I'm part of Pioneers and Dark Girls and I'm the robotics lead for Pioneers. I'm particularly interested in AI and engineering. robotics. That's what Hello, my name is Agnes Ayerga Tanga, and I'm also a member of Pi Ladies Ghana, and I'm a student of Blossom Academy studying data science. So I'm here to learn more. Thank you.
I'm Nadia Nemko. I have data management background. I'm here to learn data science. Thank you.
Hello, I'm Akim Osman, a student of Blossom Academy, and I'm here to study data science.
Hello everyone. My name is Abigail Oxford-Yambobi, and I'm the lead for Pi Ladies Ghana. I'm also curious about data. Thank you.
My name is I'm a computer science engineering graduate from the University of Cambridge. And I'm here to learn a lot of Python and everything Python.
My name is Sule.
My name is Frederick and software developer, and I'm learning data science and
Hello everyone, my name is Gideon. I'm a teacher of the gospel and I'm interested about digital everything. So I want to know how to use digital aspects and do a lot. Thank you very much.
Hi, I'm Lee Series, my name. I have a background in finance and admin, and I'm also passionate about for IR. That's what I get.
Hello, my name is Gabriel. I'm here to learn about data science. A recent graduate from UCC.
My name is Steffi. I'm actually going to.
Hello, I'm Victor, a recent graduate from the University of Ghana in software development.
Hi, I'm William. I'm a C# developer and an IT support officer at Lifestone Ghana. I'm interested in data science and AI.
Hello everyone, my name is Bernard Ejeboka. I teach computer science at Western University College, so UCC sometimes. I just love Python and all about it, so I want to know more.
Hello, my name is John Emery. I have passion for data science as well.
Hello, I'm Dawi. I'm a software developer at University Association of Africa Universities and volunteer at Global.
Hello, I'm Edem Agonyo. I'm a full stack developer, so I'm freelance. I'm also aspiring to become a data scientist. That's what I'm doing.
Hello, I'm Emmanuel, a student. I'm excited about data science, so I'm here to learn more about this.
My name is Boaji Daniel, and I'm an AI engineer. But currently, I teach data science and AI at Digital Unit. Hello, I'm Isa. I'm an aspiring bioinformatics researcher, and I believe data science is a step towards bioinformatics.
Some of the people actually inform me something. Currently a data engineer to Beg Africa. Yeah, so I'm very interested in data algorithms, but I'm also interested in this now.
We can talk about it.
Hello. I'm Sam. I'm currently working at Systems Creators of Machine Learning as a front-end guy. I did a few projects on machine learning AI also.
Hello, my name is Kiva Mwangi. I work at Get Innotized as a data analyst, and I'm here to learn more.
Hello, my name is Abu, and I'm here to explore.
All right. Yeah, I think I'll just launch. Yeah. Well, I know that one of the most terrifying things to do as a programmer is to stand up and talk in front of a group, so you all did great. Thank you. Thanks for introducing yourselves. So I'm Jon Kaufman. I am the lead data scientist for 4th IR. We are an artificial intelligence, machine learning, data science shop. We have clients all over the world. And I've been brought here by the Trestle Group Foundation to give an intro to data science and artificial intelligence here, and then I'll be teaching the Trestle Academy next month, where we'll do a lot of hands-on stuff. So what I'd like to do today, I'm going to tell you a little bit about myself. I'm going to tell you a little bit about artificial intelligence. I'll tell you a little bit about data science. And then what I'd like to do is just use this opportunity to let everyone just ask questions. So, we've got a bunch of things that we want to accomplish today. We've got things planned, but really, by and large, this is an opportunity for us to have a discussion about this. So there'll be opportunities for questions throughout the talk, but at the end, we'll just dive right in. So the Connect and Accelerate program, what we're trying to do here is to bring data scientists from industry into Ghana and then eventually beyond to really provide some one-on-one interactions that would be much more difficult to get even just virtually. So we're really excited to be doing this. I'm going to talk a lot about data science and AI. You can follow me on Twitter at JPK Science. You can tweet this TGF Connect if you want. If I see you on your phone, I'll just assume you're tweeting cool things about TGF Connect. So I just want to give a very general background of who I am, and by who I am, it's sort of where I've been. I was born in Baltimore, Maryland, which is about an hour outside of Washington, D.C., the capital of the U.S. It looks like this on a good day. It's not looking so hot these days, but that can be a different talk entirely. I went to Carnegie Mellon University for undergrad, which is one of the leading universities. I think it's actually #1 right now in artificial intelligence and data science. It's in Pittsburgh, Pennsylvania. Pittsburgh is known for being one of the cities in the world with the most amount of bridges. So I guess if you have to be known for something, that's not so bad. It was also where most of the world got its steel until about 1970, 1980, when China took over the manufacturing. It's since reinvented itself as a tech hub, so it's one of the best cities in the world for data science, for artificial intelligence, and for software engineering. It's also just a beautiful campus, so if you ever get the chance to go to Carnegie Mellon, definitely take it. This is actually University of Pittsburgh's campus, but it's a nice building, so I'll show it. I got my PhD at the University of California in San Diego. The campus has its own beach, so it's very pretty. The library here looks like an alien spaceship, but it's a great place for physics. I did astrophysics and cosmology. Cosmology deals with the origins and evolution of the universe. So as part of this, I got to work with telescopes all over the world, but especially at the South Pole in Antarctica, which is where I spent about 8 months of my life. So this is a emperor penguin here. This is me. It was, cute and cuddly looking, but they're actually pretty mean if you get close to them. And so this is the building where my telescope was in. What I'm doing right here, this is actually me. I'm hoisting up. This is a dewar of liquid helium, so 4 degrees above absolute zero. And we would use this to cool our detectors to superconducting temperatures so that we could view the sky. This was the station where we would stay. It's about a kilometer walk between the station and the lab here. There's some people taking pictures of the whole thing. Apparently it's pretty interesting watching this thing go up. There's another telescope here. This is a experiment that has photo collectors actually drilled into the ice. And so they're looking for cosmic neutrinos to hit the ice and create these showers of particles. And this is a toilet. And so now I live in New York. It's an incredible city. I highly recommend if you ever get the opportunity to visit. It's just beautiful. There's a large population of people from Ghana, both permanent and tourists. And it's just a beautiful city. And now here we are. So I've had a wonderful time here so far. I'm so grateful for everyone welcoming me to your country. It's my first time in Africa. I'm very, very excited to be here, and it is not disappointed. Ghana and Accra especially have just been incredible, and I'm looking forward to coming back next month to teach the academy. So on to more pertinent things. Artificial intelligence and machine learning are the hot topics today that you're seeing all this research going into and where a lot of the jobs are. Just very, very high level, all of this is under the umbrella of algorithms. Algorithms can mean almost anything. You probably have an algorithm for the way that you get up in the morning, maybe brush your teeth, maybe eat some breakfast, maybe go to work. That itself could be an algorithm. Here we're talking about digital algorithms. There's a large overlap between machine learning and artificial intelligence, but they can be separate. Not everything that you would do in machine learning would be artificial intelligence. Not everything that you would do in artificial intelligence can be machine learning. Deep learning is at the confluence of machine learning and artificial intelligence, but it doesn't necessarily have to be AI. And expert systems, if you're looking at AI, you'll probably hear a lot of things about expert systems. It's a totally different type of AI. I get to say what I want because this is my talk. I'll say it's an older version of AI. It's not as useful anymore with deep learning, and I'm willing to fight people on that. And then data science is across all of this. So you'll do a little bit of everything in data science. And then there's also regions of data science that are not contained within the machine learning and artificial intelligence, or even in the algorithms. Some of data science is just thinking and planning. So data science at its core is really, it's an art and a science of collecting, analyzing, and modeling data. And the goal here is to make sense of the world using data. So a lot of times you'll hear modeling thrown around, but really so much of it is in analyzing and collecting the data. So what you have here is the data science hierarchy of needs. So this is a pyramid showing sort of how useful it is and how much you do it. So at the very base of this pyramid, the strength of the pyramid comes from things like logging, sensors, having external data, getting user-generated content. Collecting the data really is the heart of data science, and it's often overlooked. I've already heard some feedback today that tutorials, they tend to cover how to model the data, but they don't cover how to collect the data, and that's extremely important. Storage of the data, moving the data. This is things, these are things that you don't often think about if you're just modeling, or even analyzing the data. What sort of database, framework are you using? What sort of database technology are you using? How is the data going to flow between, the user-generated content, like a mobile app, and the database that you need it to store it, and then the data that you're going to load into memory and process. What does that whole thing look like? Exploring the data, visualization, cleaning. What we say nowadays is we need fewer data scientists and more data janitors, people who are just looking at and cleaning the data. And it doesn't sound as exciting, but it is reliable work. Everybody needs a data custodian, a data janitor. So anomaly detection is very important, looking for data that shouldn't necessarily be there and understanding that. Then you get into the aggregation, the labeling of the data. So bringing it all together, merging different types of data and saying, okay, this is the class of data that I want, this is the class of data that I don't want. Then you can start into the learning, the modeling, the machine learning. You'll hear phrases like A/B testing going around. Very simply, it's just modifying something and seeing if it makes a difference in your product. It's rooted highly in statistics. And then on the top of this pyramid, what is sort of the most tailor-made, most advanced, but not necessarily what you'll spend most of your time on, is the AI and deep learning, but it's important to know. So getting to the guts of it, right? If you want to start in data science, where do you start today? These are really the main languages that you will come across. You don't have to be an expert, nor necessarily should you be an expert in all of these. Basically, I would draw a line here between Python and R as saying, pick one of those, Python. SQL is totally different, and then C++ you'll see used a lot. I don't really type or code in C++ to show how useful it is generally, but there is a lot of work in C++. Python, I think everyone in this room knows what Python is or has had some experience with Python. I love Python personally. I originally came from MATLAB for data analysis. Python's super easy to learn. The communities are amazing, as you've discovered, as you are part of. And you can do nearly anything, and of course it's free. That's fantastic. The only negative really is that it's kind of slow versus a C++, or especially something like a C. And there are other, as we've discussed, challenges with the interpreter lock and things like that, but we don't have to worry about that. So R it was a language developed by statisticians to do data analysis. So in that sense, it's very powerful for data analysis, but I find it to be a little clumsy. It's got a great community. It's also free. It's also slow like Python, but you're not really going to be able to design something end-to-end in your data science framework in R. You're going to end up having to go to some other language, probably Python. SQL is the prime language for querying data out of a relational database. A relational database is the main kind of database storage that you'll see for highly structured data. It's the most used language, so SQL is a very good thing to learn. If you were going to get a job, for example, at like a large bank or some large industry, they have entire jobs of data science that have nothing to do with modeling or machine learning or analysis, but just people who are able to make the right sort of SQL queries and pull the data and merge the data and generate some statistics. So while I'm going to focus a lot more on Python and machine learning, this is a great language to learn, especially for getting a good job in the data industry. C++, I think most people in this room hopefully have probably heard of, if not programmed in a little bit. It's much faster than Python. It's very widely used for everything. I have something called fewer ghost errors, where what I mean here is when something breaks, it's a lot easier to figure out why it broke. And that's based on things like static typing and the way that you have to define functions. One of the biggest cons, of course, is that this is a compiled language. So whenever you try to get it working on somebody else's computer, it's a nightmare. It's getting better with things like Docker and Kubernetes, but it's still a pain. And then the learning curve. I mean, it's just way harder to learn than it is than Python. But you'll see a lot of this. For example, all the autonomous vehicles. Tesla. There's a whole industry in San Francisco that's just doing C++ development for autonomous driving. So a dirty secret is Excel is also a really good data science language. So even I open up data files in Excel, so don't feel like you're not a real data scientist if you're using Excel. You're usually going to want to prepare some files in Excel, and then you'll probably load it in, save it as a CSV file and load it into something else. But don't feel bad if you're using Excel. Okay, so here's where you should start. There's a lot up here. You don't have to learn all of this. But this is where I would say, the Python data science, library infrastructure, by and large, Jupyter Notebook is what you're going to use. It's great. It's easily scalable. It's easily shareable. And then one of the advantages, of course, as we'll talk about a little bit later, is oftentimes you're running on very powerful machines in the cloud. And Jupyter Notebook runs in your browser as if it were running on your own machine, and all the computations are actually done on a much more powerful machine. So one of my data scientists, PhD in physics, uses a Chromebook and does all of his analysis on a cloud server somewhere else via Jupyter Notebook. So very, very common. VS Code is actually really good nowadays. It used to be total crap, unless you were programming in like .NET or something. Eclipse is great. I actually like to use Atom a lot. It's open source. It integrates with Python using something called Hydrogen, so you can run your Python scripts. And then if you're really hardcore, you've got your Emacs and your Vim. And that's the kind of thing that people in Silicon Valley will get in fights over, like literal fights, based on which one is better. I like Emacs better, but that's just me. So data analysis, these are the things you're really gonna focus on. NumPy, number one. When you're talking about dealing with data that is very structured, you're gonna wanna process it in a very efficient way. And NumPy is numerical Python. It's meant for data. Python is just totally generic. You can program anything from a web app, a mobile app, to server maintenance to data science. So NumPy makes data science possible. You'll definitely want to learn that. Pandas is a way to deal with tabular data. So it's essentially, you can think of it, it's Excel for Python. Extremely commonly used in data science. SciPy, Scientific Python, just has a ton of libraries for working with data, for doing modeling. I mean, they have statistics stuff. They've got everything. You could do, fluid simulations in SciPy, and as well as you could do data science. Dask is a framework for doing a lot of this stuff in highly parallel environments. You don't have to learn that one for a while. Most people will never come across it, but I figure it's worth at least saying, getting familiar with the term. So for machine learning, number one machine learning framework is the scikit-learn framework. So this is, it's got all the sort of regression and classification models that you'd work with. You've probably seen the tutorials. Many of you have probably worked through those tutorials and even run some of these in your projects. It's widely used throughout the community. XGBoost is a specific type of machine learning algorithm that's probably the best before deep learning, and in many cases actually even better than deep learning for tabular data, or things that are in Excel workbooks. So XGBoost is now being integrated into SciPy and scikit-learn, so you won't have to worry about it too much. Rapids is a library from NVIDIA for doing highly distributed machine learning on a graphics processing unit. So most of the scikit-learn stuff is optimized for your CPU. You tend to move into deep learning with GPUs, but you also get a boost from doing highly parallel machine learning often, and that's something like Rapids. Data visualization is extraordinarily important, especially, a data scientist's job is, partially looking at data, but also communicating the data, the results, the analytics to other data scientists, to programmers, to people with a business stake. So matplotlib, I like to think of it as standing for MATLAB plotting library, but it's just mathematical plotting library. But it makes it look exactly like something like a MATLAB or an R that has a lot of this built in. There's things like Bokeh. Seaborn is another one, just other types of plotting libraries similar to MATLAB. I like Plotly a lot. It allows you to do interactive plotting. Very easy to learn, very easy to use. There's also JavaScript bindings for it. Well, actually, it's a JavaScript library for which there are Python bindings. So if you're a JavaScript person, I recommend taking a look at it. It's built on D3, if that means something to the JavaScript people. So it's very, it's very user-friendly. And then there's things called tsne and umap. You don't have to worry too much about these, but you may want to be aware that they exist. These are ways to group data and reduce the dimensions of it. So if you've got 30 different columns of data and you want to visualize it in just a couple different, in one XY plot, you'll probably want to use something like a tsne or a umap to do that dimensionality reduction. And UMAP is a recent development. It's much faster than a tsne. But just knowing that those exist if you're ever stuck is very helpful. Deep learning, of course, what I want to talk a lot more about today. TensorFlow is by and large the #1 library for deep learning in the world, no matter what the PyTorch people are going to tell you. PyTorch is good, but TensorFlow is still, kind of kicking its ass. And then Keras is a wrapper around TensorFlow. It also supports other frameworks, but like Theano is another one that's since been sunsetted. But for example, I almost entirely write my work in Keras. Very rarely do I even have to go into TensorFlow itself. And then the other libraries that you should know, I think, are very important, because data science is really just trying to figure out, how to make your thoughts come to reality. And so you're thinking, how can I do this? And then you can Google frantically. But here's where you should start. I'm sure many of you have dealt with Beautiful Soup and Python. It's for extracting structured information from web pages, or really anything. You can deal with XML, or HTML, obviously, for websites, or any sort of structured language like that. And it allows you to be able to traverse the hierarchy structure of that data. So you've got highly dependent data, like a web page, and you can pull out all that information. So it's just great. Requests is something you'll probably end up using a lot. This is a way to make a, like for example, a RESTful API call to some server somewhere. This is great for downloading data or interfacing with other people's APIs. So used all the time. The JSON library, of course, for passing data around, storing data. OpenCV, this is a computer vision library that's built off of original C libraries. That's very, very good for image manipulation. It can be a pain to work with, as with anything that's built in C, but it's used all the time. Similarly, I tend to go with scikit image, or SK image when you import it, just because it's a little bit easier than OpenCV, and it's got 80% of what I need is in scikit image. Flask, I didn't put Django up here, but that's sort of similar. I tend to write a lot of simple web apps in Flask to host our models and to productionize them, to use them, to integrate them into other systems. And then this isn't a library necessarily. It's not quite data visualization. It's not quite something else, but principal component analysis, PCA, it's a dimensionality reduction method. If you want to look at data that's very dense and you want to just plot it to see if there are patterns, you're probably going to want to use something like a PCA. So just something, again, you can sort of Google and figure out how to integrate it. So artificial intelligence, moving forward, it's definitely a large part of data science, but it can be somewhat separate. So I like to give this definition of AI. It's a computer program that performs an action that traditionally requires a human decision. So it's really all about, is it AI? Well, does it require human judgment? Is it replicating human judgment? Is it augmenting human judgment? So when you're designing your applications, when you're designing your companies, you're thinking about, am I making a judgment call here? Is this something that I could train an algorithm to do? Versus something like just a calculator or something that's running analytics on your databases. That's not necessarily something that's replicating human judgment. Robotic manufacturing sometimes is just following a set of instructions. It's not necessarily a judgment call, but some robotic manufacturing absolutely is. When they have the fry, or chips, I guess you guys call them, right? The French fries going through a conveyor belt, they'll have a camera looking at them for ones that are improperly shaped, or they're just something, a defect in them, and a little puff of air will shoot them away. And they're using a computer vision algorithm to detect that, and that's absolutely, I would consider AI. One of the highlights here is that there's essentially two types of AI, right? There's statistical or evidence-based AI, and that's where you'll see all the machine learning come in, which we'll talk about next. And then a heuristic-based AI, which is more rules-based. And this is, when I was talking about some of the expert systems and things like that, you'll have a group of subject matter experts get together. They'll develop, what they think are the right, series of if-then statements, and then, that will sort of replicate human judgment. And now what we're doing is we're saying, forget trying to write your expertise down. Let's just let the data tell us the best way to do this. And we're finding better than human accuracy on a significant amount of machine learning projects for this. So this brings me to machine learning. My definition is, this is a class of algorithms as before, and their performance improves by being shown examples of data. So unlike a normal algorithm where you're writing it to just sort of do the same thing every time, doesn't matter how much data you send it, a machine learning algorithm is going to get better, or at least one that's operating properly, is going to get better as you show it more and more examples. So it can be broken into two major types: supervised machine learning and unsupervised machine learning. In supervised machine learning, you're providing the labels, you're providing the right answers, you're saying, replicate this, this is what I want to see. In unsupervised learning, you're saying, I've got some clustered data, I know there's a pattern in here, I don't know, what those patterns are, but go find it. And then it'll take this, something like a clustering algorithm and say, I believe that there are 3 types of users here. It says, well, these users seem to be clustered together, these users seem to be clustered together, and these users seem to be clustered together. So it'll make that call for you. Under the supervised machine learning, you'll probably see, mostly classification problems. Is there a person in this image? Is there a dog in this image? Is this potato, French fry bad or good? And then a regression problem, which is saying, given these parameters, can you guess the next number or tell me the next number? Linear regression is by far the widest used machine learning, technically, algorithm. And it's just fitting data to, or fitting a curve to data. Logistic regression is also probably the second most common. So a large portion of AI right now has been revolutionized by the influence and the extreme amount of research breakthroughs in deep learning now. And so deep learning is a class of machine learning models. So they are all statistical learning based, and they're comprised of many stacked artificial neural networks. So that's where the deep comes in. There are deep networks of artificial neural networks. Each one of these here in the input layer, you'll have your data coming in here. This is some artificial neuron. There's some connection between artificial neurons. Here's a different layer. Here's a second layer. Even this would be considered a deep neural network. And then there's some output that, maybe it's a classification, maybe it's a number. These are a couple of examples of common deep neural network architectures. I'm not expecting anyone to say, oh yes, of course this makes sense. This is the inception net. And what I'm mean by this is each one of these sort of blue and red and green blocks is in and of itself a deep neural network. So these become very, very large, very complex, very deep, millions or even hundreds of millions of parameters. And then this is something like what's called the VGG style network, where the input is an image, and you can see each one of these layers becomes sort of smaller and thicker. And this is the information essentially getting funneled into its minimum representation by these deep neural networks. And so these neural networks are designed on how the sort of mammalian brain stores and processes data. So we have in our brains, not that we have a complete understanding of how they work, but we know that there is information stored in these neurons, and these neurons get some input, and the neuron decides whether or not that input is relevant, and based on that, it will fire a signal to its other connected neurons, right? So what an artificial neural network does is it does the same thing. It has some input, it has some information stored in the neuron itself. It has some nonlinear function that decides whether or not that information is relevant. If that nonlinear function, has a successful operation defined by the user, it will then fire its information off to other attached artificial neurons. So it's replicating how human brains work, at least at a very simple, a very simplistic way. Okay, so I'm going to take a break from the slides for a second, and let me see if I can get this to run live. Has anyone seen this before? This is Google's TensorFlow Playground. Anyone seen this? One? Okay. This is a really good way to understand how deep neural networks work. And we're going to run this interactively. So it's a little hard to see right now, but it'll get a little easier. What we have here are input neurons, a hidden layer. This is the deep part of the neural network. And then two hidden layers, and then an output here. And the goal is there is some data for which we know that there are two types, right? There are blue dots and there are orange dots. Now, we, as intelligent humans, can see that the blue dots all cluster in the center and the orange dots, all cluster in a ring around it. If you were trying to solve this with a linear regression, it would not be able to do this. This is not linearly separable in this current form. What you do is you say, okay, let's say I start with something that just says all the orange is on one side, all the blue is on the other side, all the blue is on the top, and all the orange is on the bottom. Let's just start with those features, and let's let the deep neural network figure out how to classify the blue dots as the center, the orange dots as the outside. So we're going to run this, and what you're going to see is the information stored in these neurons are going to change, and the connections between these neurons are going to change as it learns the best representation for this data internally. So I can pause it here. That was quick. I'll run it again. But you can see now it's doing a pretty good job of figuring out that all the blue ones are in the center and all the orange ones are on the outside, right? And so it's done this by combining this information in these sorts of ways. You see the orange, I think, is by additive, and the blue is, I think, a subtraction. I don't recall what the parameters are set up for here. And so it creates these different sort of advanced features based off of the input features. And they get more advanced as they get combined in deeper layers. So it's a little hard to see there, but there's actually a sort of a circular shape here now based off of these. And so these connections and the information, it has now learned an internal representation for classifying this data. So let me run this one more time, and you can watch it learn. And here, you're seeing it starts making some guesses. It calculates how wrong those guesses are, and then it's something called backpropagation. It propagates that error through the entire network until it gets better and better, and you can see it just very rapidly discovers a better representation, and then it flattens out. So when you're training these models, you're going to care about this sort of training accuracy, test accuracy, validation accuracy. These are phrases that are going to get thrown around. So let's go for something that's a little easier. We can understand that we'll probably want to see something that's like a line here. Let's see if the neural network can figure it out. Well, that was pretty quick. It's a very simple data representation. But let's go with something really hard. These sort of spirals, right? How would you design a model that can classify spirals without knowing anything about the underlying data itself or the underlying fundamental theories as to why these would be spirals? Let's see if it can figure it out. Nope. So let's make this more interesting. Let's add a bunch of hidden layers. Let's add some more advanced features. And let's see if it'll figure it out. It's starting to try. It's freaking out. Interesting. Let's mess around with this. This thing's so much fun, I highly recommend it. Let's add a bunch more neurons. Oh, I think it's figuring something out. So this is interesting. I'm going to pause it. What you're seeing right here, it's figured out that this is orange and that this is orange. You see how there's this orange gap in between the blue? This is a really interesting lesson for the real world. you may not know the representation that your model has figured out. So the fact that there's missing blue here, it probably thinks that it's okay to have an orange in here. You're going to find that models will perform very strangely sometimes in the real world when they get data. Imagine there was a blue point that we added right here. This model would classify it incorrectly. So it's very important to really understand these deep neural networks. And we're also learning something live here, which is that these can be very fickle. They can be very difficult to train. I can't tell you the right way to organize these neurons. This requires a lot of experimentation. There's a lot of science to this, but there's a lot of art to this. So when you get really good at it, and I haven't messed around with any of the hyperparameters here, I'm just sort of playing around. What makes a really good deep learning data scientist and deep learning engineer is looking at something like this and understanding, well, why is this incomplete? What can I do to improve these models? In the Trestle Academy, we're going to talk a lot more about machine learning, and we'll definitely train some deep learning models. I'm thinking at least doing some computer vision and probably some natural language processing as well. So, back to our regularly scheduled slides. This is a little tough to see. This is a representation of what's actually happening in a deep neural network. There are 10,000 artificial neurons in here with 3 different hidden layers, 3 different sets of connections between these layers. On the input is the MNIST data set that you may have heard of. It's the handwritten digits, and it's sort of the hello world of computer vision and deep neural networks. And so what you're seeing here is there's white dots and there's black dots. The white dots represent a neuron where that information is considered relevant to classifying that digit. The black dots are where that information is considered not relevant, and therefore those neurons don't fire. And at the edge here, you'll see the output, so it's correctly classifying all these. So this is a very simple deep neural network, but at the heart of it, this is how all deep neural networks run, is that there's information that's being passed from the input all the way through to the output, and it's, these neurons are deciding whether or not to essentially fire, or whether or not that information that's stored is relevant. So why is artificial intelligence and deep learning and machine learning so popular today? We're at a very fortunate time in the history of computer science and IT, in that there's more data now than there's ever been. I think we're now something along the lines of we generate more data per day than was generated, I think, from the dawn of civilization to about 1990. So it's just incredible how much information we're generating. So, naturally, cell phone technology, almost everybody now has a cell phone in their pocket. That is a massive source of information. The internet being, entirely global now and with a massive user base, specifically social media data is allowing people to do things that were not even possible 5-10 years ago. And then, cheap and easy storage. It's one thing to have a ton of data, but if you can't store it, then what's the point? Nowadays you can get extremely cheap data storage and also extremely powerful memory, which brings me to the next point, which is you have improved processing power. And I'll show you on the next slide a visualization of what this means, but by and large, graphics processing units, or GPUs, these were built for gaming. Of course, a lot of intelligent engineers figured out that, well, hey, gaming is just manipulating matrices. Working with data, it's also just manipulating matrices of data, arrays of tables. So why don't we try using it for GPUs? And now you can get highly parallel, very, very fast information processing for things like deep learning, machine learning. And with things like computer vision and natural language processing, you can't even do them without training on GPUs. So one of the things that we're working to secure right now through the Trestle Group Foundation is access to cloud-based GPU storage for everybody who joins the Academy. So we'll make sure that you're working with really powerful machines. with that, increased RAM is extraordinarily important. You have to store all this data into memory to do anything with it, and I can get a terabyte or even a couple terabytes of RAM on Amazon. I can rent that hourly. So it's really incredible. What people used to call big data isn't really all that big data anymore. You know, if you can store it into RAM and all you need is a few gigabytes worth of data, you know, you don't really need to you know, develop these massively parallel MapReduce Hadoop stuff like you used to have to do. And then faster networking, you know, being able to transfer data very quickly between different machines. You know, this has led to a significant revolution in artificial intelligence. Another thing I like to point out here is, so this is 2006, here was 2018 where it stops, and this is the essentially the floating point operations per second of the graphics cards. And you see this sort of massive spike. And what I like to say here is this is about where the AI threshold happened. This is about when graphics cards became more powerful than just using a highly parallel supercomputer. And this was about, what, 2012, 2014? So we're not even 10 years into this, into the really advanced revolution of deep learning and AI. So, you know, if you're getting into data science now, I think it's the best time to get into it than any other time in the past. So what do we use it for? Natural language processing, of course, is probably the most widely used way that you'll see deep learning. Machine translation, you know, if you're traveling to you know, many different countries, this has definitely saved my butt many occasion. I've got it on my phone. Dana's got it right now, but Google Translate lets you download for free their machine translation tool, and you can even use their computer vision. So hold it up to a sign written in German, and it'll translate it to English. So it's extremely important. Information retrieval, being able to sort of classify documents and extract that information in an ordered way. Sentiment analysis, you see this happening in all sorts of user reviews for Amazon, Netflix, you know, any e-commerce site or anything that depends on user reviews. It's got sentiment analysis baked in now. Information extraction, so let's say that you wanted to look at 1,000 different documents and you wanted to determine the relevant information to your business, right? One of the things you can do now is you can send this through a natural language processing AI and extract a lot of this information. So instead of having to read thousands of documents, it can summarize this for you. So this is a huge time saver. This is why you're seeing things like you know, healthcare and law. Those are some of the industries that are most that can be most impacted by the advent of deep learning and AI. And then question answering, customer service, you're seeing this. Many of you, I'm sure, have built a lot of websites. You know, if you wanted to throw a chatbot in there, you know, for better or for worse, that tends to be people's first, you know, the first time they experience AI. So some of these chatbots are doing a really great job. You know, it's sort of funny, the ones that are doing a poor job are the ones that you're going to remember. The ones that are doing a great job you'll never think about because you don't even realize they're a chatbot, right? So one of the things that I think is most exciting and most relevant, especially for data science, is that data science at its heart is dealing with manipulating data. You know, language in and of itself isn't really data. It's not really designed for data, it's designed for communication. So we have to figure out a way to represent language in a way that allows us to do essentially math on it, you know. So what I've termed language algebra here is you can use these word vectors or sentence vectors or document vectors where you take a word and you embed its representation into a much higher dimensional space that is now mathematical. So instead of saying, you know, every word that I'm saying is just, you know, you just count the number of times I say different words, there's no way to make a relationship between, for example, day and night. it would think day and night are just as related as, day and lobster or something, right? So it wouldn't make any sense. But if you encode this information in a vector, a highly structured mathematical representation, and you use some machine learning to let it figure out what the best representation for that information is, you can then start to do algebra on this. So, for example, it'll know that, if, say, take the vector for man and, have it related to the vector for king, and then subtract man, add woman, it will know that the way that man maps to woman is similarly to the way that king maps to queen. So you're able to do a lot of these very interesting things where you may not know the exact representation or the exact context, but you're able to manipulate the language in such a way that now gives you the ability to do things like knowing that this is just a Google search result. It knows that people who type London might want to know the population, might want to know time, weather, bridge, broil, fog, of course. So knowing that things like this are actually related allows you to generate very powerful tools. Similarly, probably the best use of deep neural networks that you'll see these days is in spam detection. This stuff works so well that you don't even realize it's happening anymore. A lot better than back in the 90s. So you can train a classifier based off of those word representations and saying if certain words show up a lot more or certain representations show up a lot more, it's probably likely spam versus likely mail that somebody wants to see. So this is a very common thing that data scientists will look into. This is an example of that information extraction. So let's say instead of a paragraph, you had thousands of documents. You can apply this sort of entity extraction and information extraction, and it'll just give you the highlights of this. So, if we're learning things about London, a lot of people, and myself included, didn't realize that London was originally founded by the Romans. I just thought it was always a British place. So, extremely powerful for collecting business insights. So computer vision is another major area of this. In computer vision, a lot of times what you'll see is sort of scene detection and object tagging. So I'll show a live example of this in a little while of how to classify and put bounding boxes around different things and different people. It's also used a lot for biometrics and facial recognition, sometimes for better and sometimes for worse. There's a lot of scary things happening in China right now with this deep learning for Face ID. But it's also doing things like emotional analysis. So you can imagine if you want to understand how your users are interacting with your product or in your shopping centers, things like that, you can monitor that and actually quantify it so you can measure it, something that would traditionally be very difficult to measure. Autonomous vehicles, computer vision, this is happening all the time. I'm seeing these on the roads back in the US where people are reading a book or reading a newspaper while they're driving or their car is driving them. Waymo from Google, Tesla, Uber's got theirs, Lyft is working on theirs. What's it called? Zoox, I think. There's tons of these computer vision, autonomous vehicle companies. So this is surprisingly easy to do. It's also surprisingly hard to do right. So you could train an algorithm in a very short amount of time that could build like a robot that would be able to navigate around this room. But roads are very complicated, and especially driving through downtown Accra, these roads can be very interesting. And they are going to be a nightmare for these computer vision algorithms. So this is actually something that my group worked on. This was cancer detection. What we would do is we have, these are digitized slides of biopsies from lymph nodes of patients who may or may not have breast cancer. And so we get these very big files. They're about a gigabyte per image, and there's usually 10 of these per person. And we're analyzing these files for regions where we think that there is a high likelihood of detecting cancer. And so we break this up in a sort of clever way so that we can parallelize it. We train an algorithm to detect these individual cells. We run these through this deep neural network, and at the end you get this heat map that says, in each one of these regions between sort of 0 and 1, what is the probability of these cells being potentially cancerous. And so this is something we did very well. I think we were able to get something like a 95% accurate detection for cancerous cells. And you're going to see a lot of this coming in the next couple of years. Some of it's already working today. And this is where, specifically one of our goals in working in Africa is being able to develop African data sets and African companies who can build these things to improve the healthcare for the local African communities. So you can imagine, working with the local Ghanaian hospitals to develop these data sets that help, people not just in Accra but in remote regions access to better healthcare. This is a fun application. So this is the famous Van Gogh Starry Night painting. It's in New York, so if you come to New York, I can show it to you. And this was Google's Deep Dream. So this was an earlier version of some of the deep neural networks. It was trained on a lot of pictures of dogs, and so you see this sort of dog slugs, they call them, like these weird faces and eyes and feathers and things. But this is just sort of a representation of how the computer algorithms see the world when given an input of Van Gogh's painting. So this is used a lot for this sort of image transferring. So this is the famous Mona Lisa, right, by Leonardo da Vinci. They made it look cubist, like a Picasso. They made it look like a Van Gogh painting. They made it look like I think this is a Renoir, so Impressionism. So what you're able to do now is something like this, and these apps exist, and you could build them yourselves with the knowledge that you'll get, some that you already have and some from the Trestle Academy, is you can input an image and have it generate, based on, I want it to look like this, you get the AI output, and it takes the representation of the information in here and makes it look stylistically like something else. So this is a lot of fun to mess around with. I mean, I love this. You take one type of flower and you want to make it look like a rose, and it's incredible. It keeps the I don't know what type of flower this is. Let's call it a carnation or something. But it makes it look like this this sort of dew-soaked rose. This is used by Snapchat. This is used by Facebook. So this type of deep learning is incredibly powerful. And it can also be very lucrative. So the first AI-generated art auction, not the first AI-generated art, it sold for $432,000 US at auction, which was about 10 times more than anyone was expecting. And even that was a lot more than I think it deserved. But what this is interesting is this is actually signed by a mathematical function and not a person. So there's a lot of controversy around this because who gets the $400,000 when it was essentially a open source developed algorithm that an art collective put together. All right, this is a fun one. So both of these faces, I'm just going to go and tell you the answer. Both of these faces were generated by a GAN, by an artificial intelligence network. So this was only about 6 months ago that this came out. I'll even show you. Oh, there was a picture taken there. So. I know the guy on the left. Yeah, I know. That guy owes me money. So this is another example of this. They've taken a source image. They say sort of take the qualities that you see in this image and make it look like the qualities you see in this image. And it's just incredible. All of these, none of these people are real. None of these people exist. And yet they are photorealistic. I mean, this kid's a little weird looking to me, but a mother could love that face, I'm sure. It's just absolutely incredible what's happening. So you can today use algorithms that can do this from your own machines. Now, you may need to use a GPU machine, you may need to use cloud resources, but again, during the Trestle Academy, we'll walk through, sort of from front to back, how to not necessarily run a GAN like this, but how you would want to do it based on the skills that we'll give you. So just sort of wrapping up here, there's 4 things that you're going to need for doing data science and for doing machine learning and AI. And it sounds a little silly, but sometimes it's very helpful to have just very simple structures around these frameworks. So you need a use case. And that's one of the things that I'd like to talk about with a lot of the people in the room is based on what you work on, based on your industry, what are you seeing as something that data science can help, or machine learning can help with, or AI can help with. Once you have that use case, you have to think about what data do I need? Does it exist already? Do I need to clean it? Or do I have to start generating it? Do I have to start logging user, how they interface with the algorithms, or sorry, interface with the platform? Do I have to go and download images from the internet? Do I have to mark these images up? Then you start thinking about what algorithms do you need? Everything from what sort of statistics are relevant to what machine learning algorithms, or should I use deep learning? What kind of deep learning algorithm? What is that? What's the architecture of this deep learning algorithm going to look like? And then of course you need compute resources. So you have to think about, am I doing this on my laptop? Am I doing this on a cloud machine? Am I doing this on a giant highly parallel 500 GPU rig that costs $10,000 an hour? And for some of the use cases, that absolutely makes sense. If you're talking about working in the finance sector and you want to understand what the best timing is for trading securities or Bitcoin or something, you're going to want to spend a lot of money on compute resources because you'll get more money back. So when you're training a model, this is just a helpful framework for it. Is you've got your input, you've got your algorithm, and your algorithm has an output, and you have to, in a very iterative process, you want to validate this. So it's not just a one-way, from input to output to the product being, or the model being deployed in your product. There's a lot of back and forth here, and this is really where your value will come in as a data scientist, is understanding how to iterate on this, how to modify things, what goes into your training data set versus a validation data set, what those things are. And that's, again, stuff we will talk about at the Trestle Academy. You will definitely understand some of the pitfalls for splitting a training data set and a validation data set. So the AI toolset, data science, machine learning toolset hierarchy, this from the top is sort of the easiest to implement to the hardest to implement, and then the flexibility and customization. The top is the least flexible, the bottom is the most flexible. You've got your web-based machine learning platforms. These are things like Amazon SageMaker, your Google Cloud AutoML, some of the H2O.ai stuff. You've got your third-party APIs that run some of these things where you're just sending your images. So this would be like GCP, the Google Cloud, or Amazon AWS, or Azure, or any of these, where you're just sending an image, or you're sending text, or you're sending data, and it's got a pre-trained model, and you're just interfacing with that. Then there's things like high-level AI code libraries. This is Keras. PyTorch could be considered this. Low-level AI code libraries, things like TensorFlow. And then your DIY AI. There are times where you may want to create a entire neural network architecture or machine learning architecture from scratch in like C++, especially if you're running on edge devices. That's becoming less necessary nowadays with Python and with some of these edge compute things, and I'll show you an example of one of these. But by and large, there are data scientists that work in all 5 of these, right? So if you want to be a C++, building everything from scratch, I got people you can talk to that are hiring for that, right? If you want to work sort of, I'm in this level, actually I would say I'm in these three, right? If Microsoft has a tool that does it, I'm just going to use Microsoft's. Otherwise, I'm going to build something in Keras. If I can't do it in Keras, I'll do it here. And beyond that, it's probably not something that we need to work on. Many people will be in, I mean, to be honest, right? Many people will actually just be familiar with maybe these two, right? Where you say, I'm a data scientist, I'm just going to chug through my data, I'm going to clean it, and I'm just going to send it to something that does a lot of the machine learning without much input. So there is room for all types of data science experts. The industry is very excited. There are more job openings than there are trained people. And the benefits and the pay is great no matter what you do. So, all right, with that, I'm going to pause. We've got some conversations we're going to have with everyone in the audience and some of our partners. I'm going to run through a live AI demo, and the point of this demo is we'll essentially teach you how to build this in the Trestle Academy. And then I'll announce a little bit about what we're going to be doing in the Trestle Academy, including some of the prizes. So let me pause here and feel free to fire questions at me. I prefer you raise your hand though, so no, everyone speaks at once. Yeah, Boo-Boo. Oh yeah, let's get the microphone.
First one is why is what the preference of GPUs? Basically, why do we have to use GPUs instead of CPUs? That's the first one. What's important? What are the advantages? Can you use CPUs instead of GPUs?
I came prepared for this one.
So, and then the next one. I am a new. Is there any sort of framework for learning, like what languages do I need to know or recommend? Are there projects that I should take? What should the projects touch on? So that if I want to get to where you are without going through the traditional university model, I can actually get closer. And then the third one is how essential is the math skills in AI stuff. Yeah.
Okay, great. So the first question is, essentially, what's the difference between a CPU and a GPU? Very, very high level. This is how your CPU works. You've got essentially your memory. There's this cache. Don't worry about it. It's essentially a way to more efficiently reference the memory. Some controller, and then these ALUs, which are just the ways that that's an operation. So let's call this a quad-core CPU. There are 4 ALUs in here. So it can do sort of 4 mathematical operations at a given time. A GPU, here's its memory, it's got its cache and its controller, and then each one of these is now one of those math units. So you can see that a GPU can handle a significantly larger amount of mathematical operations at once. And so this is designed, you can imagine this kind of looks like an image, right? Each one of these can be a pixel value in an image, and it was designed to handle, modifying images on your screen for gaming very quickly. So when you're dealing with highly parallel data, it can be much more efficient to do these very simple mathematical operations on a GPU. So when to use a GPU versus when to use a CPU, if something can be if something's highly interrelated and requires what's called sequential programming, every step depends on the previous step, you're not going to be able to parallelize that to a GPU very easily. If you're dealing with something that is very highly parallel, so for example, multiplying large matrices together, multiplying vectors together, doing the same thing except on multiple different types of data, that's where you're going to want to use a GPU. So by and large, all the programming you do is going to be compiled to run on a CPU. You need to use special things to run on GPUs. The main library for this is something called CUDA to work with the NVIDIA GPUs, which are the main ones that you're going to want to use for this stuff. So